Good afternoon, everyone. Welcome to the first robotics colloquium of the quarter. It is my pleasure to introduce Chien-Min Huang from Johns Hopkins University. Chien-Min and I actually overlapped in our master. He was doing his master's, I was doing my PhD back at Georgia Tech, and we've been crossing paths quite a bit since then. Chien-Min went on to do his PhD at University of Wisconsin and a postdoc at Yale. He worked with some very famous people in HRI, but now he himself is very well known. We just last week we were at a workshop giving talks together, back to back. But I'm really excited to have him here and talk to you all.
All right, thanks, Maya. Very happy to be here. Thank everyone for coming out. I'll preface a little bit. Sometimes I'll cough. Everything is okay. It's just I got this little cold from my little one. She recovered in 3 days, and I'm still coughing, but nothing serious. So today I want to talk about human-machine interaction. We think about how do we design these assistive think about them as collaborators. But I want to start with just step back and think about the broader technology landscape. Right? So on one hand, we have machine being used as a tool, just very precise, very accurate, but not much in terms of intelligence. On the other hand, we have machine as an autonomous tool that does things pretty much fully autonomously without human intervention. And we see this in warehouses, manufacturing. There's not much interactions between humans and robots. Right? You see this person that just stay outside of the cage. But my work is really in the spectrum somewhere in the middle, where we start to think about machine as collaborators that can work with people more closely. And we think about this in close proximity collaboration in the physical domains, but we're also seeing this moving out of traditional warehouse and manufacturing setup to a more people-facing environment, right? Hospital, supermarket, hotels. And these machines are also moving into more personal spaces, right? Thinking about in the home, home care, doing education and learning with children. And all of these are also coming in different forms in terms of embodiment, right? So we start to see more virtual assistants or smart home devices, chatbots, virtual avatars, sometimes no embodiment as embedded AI assistants to support human decision making. And not surprisingly, given the growing power in computing and AI, is really promising a near-term future for these human-machine collaborations. But if you think about this human-machine collaboration as a design space, it's very rich, right? So here's one example of using human-robot collaboration as an example, right? So machines could have different embodiment, different forms. It could be just a manipulator. We also look at more like social robots or add social elements into traditional mobile manipulator, even without physical human forms as a smart speaker. And this different embodiment affords different type of interactions. A lot of my prior work in this space is looking at how do we design behavior for these machines, right? So for example, for robots, how do we think about eye gaze behavior, gesture, and multimodal communication? So it just shows you that how embodiment matters in a lot of interactions between humans and machines. But not just that. Besides embodiment, we're thinking about the quote-unquote intelligence behind it, right? So modern machine learning techniques are pretty opaque in terms of how they generate behaviors, especially in the language domain, right? So, and this shapes the way people interact with it. On the human side, it's also there are some elements involved the way people think about machines, right? So this is comes to cognitive biases. People might have this over expectations of machines, over trust, improper reliance. So all these factors shape the dynamics of collaboration and interactions. And there's also this contextual element to the task, right? There might be time pressure around the task. They are working together. The nature of the task, high stake, low stakes, potentially power dynamics between the person and the machines. So if you think about this design space, it's pretty rich and pretty nuances. And the question is, how do we think about all these different variables and when it comes to designing collaborative machines. And if we don't do it right, there will be interaction breakdowns, compromised team performance, and then lead to little adoptions. So this just shows you, the rich space it is. In the past few years, my group has been doing a lot of basic empirical research to really understand the dynamics of humans and machine when they work together. And this understanding, we take this understanding and then start to think about how can we use this understanding to design and develop new interaction methods to support machines to work with people. Right, so in my group, we do a lot of user studies to really understand empirically how people interact with these different forms of machines. The way we go about this is very person-centered approach. Usually, we have these 3 different stages of research processes. We start with understanding how people interact or how people behave. And this could be in the lab, this could be in the field, this could be during one session or multiple sessions. We take that understanding, we build system prototypes, and this could be autonomous systems, operate fully autonomously, or wheels of ours that are controlled by a human operator. We take that prototype back to participants to really evaluate how people interact with these new prototypes. And again, this could be in the field, this could be in the lab, over one session or over multiple sessions. So today I'll give you some examples that highlights different phases of this research process. I want to structure the rest of the talk around these 4 topics where we start to think about designing these machines that, quote unquote, becoming teammates. They are not teammates yet, but becoming teammates. The way we think about this process is 4 different stages, right? Onboarding, right? So you have this new person coming in, you want to onboard the person, you want to teach the person how to do the task from your point of view. And during the collaboration, you're not just doing on the task, there's also social elements, right? So small talk to build up this teamwork, this rapport with your collaborators. But even with that, there might be errors that happen. So how do we think about interaction mistakes during the collaborations? Toward the end, I will talk about some of the things that we're thinking going forward beyond these 4 different directions. So I'll start with onboarding. And this is really, if you think about human work, there's usually onboarding process when there's a new member comes in. So we thought it might be, only make sense when we think about onboarding the machine members, right? So we started with this very simple task, and this is during COVID, so this is a simulation one online. It's a cooking, pizza making task where you have this robot that will bring different ingredients to the humans, and human will use the ingredients to build the pizza. But before doing the task, we just add 2 onboarding tasks for the participants. One is just calibrating the robot, right? Drag the robot and go through different waypoints as if you are calibrating the robot. The second thing that we ask participants to do is to provide a demonstration of the task, right? So drag the robot, go to the fridge, pick up ingredient, and go through this path, and then place it on the table. So just do these 2 very simple onboarding tasks. This onboarding task has nothing to do with the performance of a robot, just purely just doing this. And interesting to us that just by doing so, people have greater perception of their teammates, right? They think that the robot's more committed to the teamwork. They just feel like they have a better team dynamics with the robot. Again, this is pure psychological. There's no actual performance change. So with this, we thought, well, maybe if we do things like this for the physical robot, there will be some benefit to onboard, quote unquote, the robot as a team member. So this is where we start to think about how can we get users involved in task demonstration and task programming. And this is very similar to a lot of Maya's work in the space of end user programming. Yes?
For the previous slide, can you talk a little bit about how you got that metric for seed teamers?
Yeah, so this is a custom built scale. So we are not using established scale. So we have a few items. I think the details should be in the paper, but we have a few single items, and then we construct our own scale.
Thank you.
Very good. So we start thinking about, okay, this onboarding task can be simple, but it's potentially very powerful for teamwork. So we started thinking about how can we get user more involved in this whole process. But the thing we learned is actually it's very difficult to provide a task demonstration and quote-unquote program robots. So we have a huge line of work in this space to think about how to get user involved in the robot programming. It's very tricky, very tricky. So the example I'm going to show you here is that we bring the robot into people's home, older adults' home, say, because the backstory here is that we want to build these assistive robots for older adults to age at home. Right, so we bring this system to people's home, say, given this system, what kind of tasks you would like the robot to help with, and they will just come up with a task of, in this example, it's like cleaning the surface. But you will see it's a very tedious process where they need to provide demonstration and go in between task demonstration as well as some sort of logic specification. It's just not a very straightforward process for everyday people, especially older adults. But it's a good understanding of what kind of stuff, tasks that older adults would want. We did quite a bit of this. We look at different platforms, different age group, different setup. It's hard to see, but it's pair programming. But overall, it's not a very easy task for people to do if we want to use this as an onboarding task. So not just about switching between different modality of programming, but also just even demonstration to be able to provide a very precise fine-grained demonstration is very tricky, right? So here I'm showing you is, people use a lot of force, but then the robot didn't change quite a bit because they are not familiar with the kinematics of the robot, and just like this is a place where people struggle. So with a lot of this understanding of people struggling with quote-unquote provide good task demonstration and programming robot in general, we started thinking about how can we make this process a bit similar, not similar, simpler for the participants, for people. So I'm going to show you some of the system we built. I'll go through this very quickly. For example, we think about programming by situated illustrations, right? Without programming, I will just use natural gesture to specify the task for the robot, right? So this is a top-down projection systems, turn everyday service as a programming service, right? So person can specify where the target areas of objects are, and then target area. So you can do very simple pick and place, right? So here's the area of objects you want to pick. Here's the target location. Go. And I'll show you in a second that this can actually do quite a bit of. It's very expressive in terms of what kind of program you can write. Oh, right. It's not really writing a program. So we compare this with just typical UR5. If you get a UR5, which is the robot, you take manipulator UR5, the manual, you compare this our situated programming approach with this UR5 traditional methods, you will see it's much easier to complete a task. People are less likely to make mistakes. Here's an example of what you can do. What else you can do with the system? For example, you can do some classifications of the system, right? The yellow object goes to the yellow box, blue object goes to the blue box, and then there will be an area where once the person finishes something, we'll put into that area. The robot know once something in that area can move on to the next task, right? So think about this as robot helping the person to classify the objects. The person might do some inspections or assembly. Once the person is finished, say, no, this is done, and the robot will move on to the next one. So we can use this projection-based approach to do quite a bit of different things, but the goal is to really bring down the barrier. We also look at this idea of Photoshop for demonstration. A lot of demonstration is continuous, right? So we're thinking, how can we discretize this demonstration to waypoints, and then for people to quote-unquote edit and improve the quality of demonstration. Because otherwise, if we don't support editing, what people usually do, they'll just redemonstrate. And again, they'll give you a suboptimal demonstration. We compare this again with traditional UR5 programming methods, and saw that it's actually much easier to use this quote-unquote demo shop as a way to editing program as opposed to redemonstration. People have a better sense of how to use these kind of systems. So we have been looking at some of new interfaces, tools to support people in this process of task demonstration. But then large language model came, and it just changed the whole way we think about this. So traditionally, if you think about robot programming or task demonstration, it requires years of training, a bunch of expert users to do it. And then we move to this era of end-user programming, which I just talked about, right? We provide tools, interfaces, and assistance throughout the process to make it easier for people to do it. But still, the tools, interfaces we provide are, it's one way, just make it easy. But at the end of the day, still the end user needs to specify the logic and all that. It's not collaborative. It's one way. You specify. It's just easier for you to specify. Large language model came. We started thinking this process can be more collaborative, right? So now the process is you have end user developers prompt your large language model. Large language model gives you code. You might interpret it. You might simulate it. If you don't like it, you will repeat this process. So it's more collaborative. Like your AI model gives you some ideas. You see if you like it. If you don't like it, you iterate this process. So it's more collaborative. So we're start to thinking about how can we make this more collaborative process to improve user involvement in programming. But if you think about this process, there's a lot of embedded knowledge that we ask participants to do, right? So be able to prompt, be able to write, run code, connect to the robot and all that. So the first thing we did is let's simplify this by providing a one-stop system that allows people to program robots through language, right? So we build these systems that just combine everything from the user point of view. It's one click, and then start to ask the robot to write programs, right? So we integrate conversation elements, system executions, simulation, and all that. And then if they want, they can still edit the code. So we build a system. We take this out just to do some exploration to see if people can use it, right? So the scenario that we have in mind is to use this system for life scientists, right? So thinking about it as a biochemistry scientist, they have a lot of things they need to do in the lab, right? So very tedious and repeated actions. Like, you need to pull this into this, and you mix it, and you repeat. So we think robot might be helpful there, right? So that's why we contextualize a lot of our experiments in life science lab. So we have this system. We give it to novice, which is the actual scientists from biochemistry labs, and expert just robotics students. And we just see both of these groups, they can complete a task using these systems, but the way they use it is very different. Life scientists, they don't really use the editor. They just reprompt if there are some mistakes or things they don't like. Versus expert, they was like, if they don't like it, they just go back and just edit the code as opposed to just reprompt it. Because of the whole science protocol is very repetitive, so in principle, they can actually write the general functions to do it. What we saw is for life scientists, they don't do that. They just prompt it every single time to do the things. Versus robotics students, they will just they prompt the system to write a general function in order to reuse the function. So in principle, this actually works great. But in practice, there are a lot of caveats. So we also learn a lot through this process of incorporating large language model into robot programming. Similar task, trying to mix different mediums from the life science lab. Similar process. What we found is there are so many places where things could go wrong. Right? The blue part is the arrows in motion planning, which is out of our hand, just so we don't care about that for now. The green is error in interpretation, right? So the code generated by large language model, they just have syntax errors, missing libraries, and all that. And all of that can be caught by a compiler to a certain degree, right? So it's easy to spot. The way we fix it is we write verification code to verify those code generated by large language model. So we can fix those like missing library and syntax error. What's really hard is we call execution errors, where it passes compilers. It's really hard to spot mistakes from the novice point of view. But when you actually run the code, it just creates mistakes. So for example, and this just, the compiler cannot catch that, so it's just difficult to do. So errors such as, you'll make up, numerical information, right? So even though these are provided already, because a lot of physical manipulation involves, dimensions and all that, right? So anything involves numerical values, it got messed up very easily. We also found that large language models tend to make up steps, right? So for example, have these unnecessary steps, like open the gripper in the midway through their whatever movement. It's just unnecessary, but it's still past the compiler. But it's really hard to spot if you don't run the code. So we did this test with different large language models, and it's fairly new. It's like maybe 1 month ago, so the models are pretty up to date. And the problem is please write a Python program function to pick up this cylinder, and then pull the content into this beaker, and after that, put the cylinder back to where it was. And across the board, we tried this 10 times, none of the language model will work with this. It creates different type of errors that I just talked about. So we have to do something empirically to improve this. So the thing we try is to be more articulate about the actions, right? So make sure you place the object back to where it was on the table, and then open your gripper, right? So you just need to be very articulate about the action, even though it's most people would assume that you have to put it back before open it. But for this, we need to be very articulate. Give me a second, and then I'll go back to you. So even just with this little trick, it improves performance, right? So it gets more success. I mean, there are still errors here and there, but overall we see some performance improvement. Yes.
Yeah, just to clarify, is the text that you showed in the slide, was it fed into the language learning model, or?
Oh no, it's fed into it's written by the user. So this is the user input to the language model. You can actually write it in a more free-form methods if you want. It takes fairly robust in terms of interpreting your input. But overall, we are seeing this paradigm shift to be more collaborative process when it comes to involving users in task demonstration and programming robot specifications. And again, this is, in our example, fairly positive ways to improve onboarding experience. So next, I want to talk about shadowing, right? So you onboard a member, and hopefully the member will start to shadow you and do the task in a way that would make sense to you as a collaborators. So the way we contextualize this inquiry is just a simple question: what if the machine partner can channel the human's perspective during the collaboration? So I'll use this very simple example where the person is building this children's IKEA's children's chair. It's very simple. We simplify a lot of perception by using AI text. There's this first-person camera that the person is wearing, so that we can get really the first-person view of what the person is looking at during this process. And the goal is to understand how people would do this task. So later on, when the machine partner is going to help, will help in a way that would, easy for the person to do. Right, so we collect a bunch of data like this, which I'll show you in a second, of people building this children's chair. During the building, we start to reconstruct the task representation, right? So which pieces they start with, how do they fit the two pieces together, how do they put the screws in, and all that. They just keep growing this tree. So we will have a task model represent what would be quote unquote ideal way and user-centric way to build this chair. And then during the human-robot collaboration, the robot will present the different pieces in a way that would be more human-centric to the human partner. So that it's easy for the person to put different pieces together, much easier for a person to screw the pieces together. All right, so this is what it looks like during the data collection. We just have this first-person view to capture how the person would do the task. And people do different postures for insertion and screwing. So here's one example of the robot using the human's demonstration as a way to present and collaborate with the person.
Please screw the two parts together.
So the robot presented, so this is what a person would prefer. So it's fairly easy for the person to put these two pieces together. And we compare this to a standard way, which is based on IKEA's manual, like what it looks like. So IKEA manual will look something like this. And you will see the person sort of like have this struggle to put the two pieces together, have a lot of unproductive movements. So this just shows you on the IKEA manual, this means it's easy for a person to put together. So if we look at the difference between these, we see that people have less unproductive hand use when the robot presents the items and structure the pieces in a way that would fit the person's working style. People also think the robot is more considerate and it's being a good teammate during this process. So this shows that it's important to consider human perspective during the physical collaboration. Yes.
Are those poses that the robot uses to help the person, are those pre-calculated, or is there any option for like live human collaboration while doing the task?
Yeah, so for the example I show you is pre-calculated. So we have a bunch of people coming in, we learn a model, and we have a different group of people coming in, and then we just reuse the model that we learned. So there's no live adaptation for the second group. But yeah, that will be a natural extension of that. All right, so I want to move on to talk about social interaction in the physical collaboration and the power of small talk, right? So if you think about this human-robot collaboration in a serious work environment, it's not just working on a task, right? So if you think about human workers, they are not just working on a task without talking. People usually work together, they talk, they chit-chat. So we're thinking if we want to have a robot collaborators and assistants, it would also make sense for humans and robots to have some sort of small talk. So we just started this exploration. It's fairly new. And the question that we ask is, how might small talk shape the dynamics of human-machine collaborations? Right? So we want to start with, how do people react? Do people react to small talk at all? If so, how do they react? So I want to play this video of the kind of interaction that we got. So this is a robot that will fetch different pipe to the participants. Participants will take the pipe and take a joint and start to put 3D structure together. There are some instructions on the table. So that's a setup. Let's take a look.
Bring me a green pipe.
Fetching it now. By the way, do you like to travel?
Yes, I do like to travel. Do you like to travel?
I arrived in the U.S. from Germany in a large box.
Bring me a yellow pipe.
Fetching it now. Apart from that, I have not traveled much myself.
So do you like United States or Germany more?
I do not have personal preferences. I am just here to assist you.
I heard Germany has good chocolate.
The person starts to get involved in this very meaningful engagement with the robot.
Bring me a green pipe.
Retrieving the pipe. That sounds wonderful. Is there anywhere in the U.S. you would like to visit?
Start to ponder very carefully about the question.
I've never been to Las Vegas, and I heard that that's a fun city to visit. Bring me a green pipe.
Fetching it now. What do you hope to do there?
Probably gamble. So go to the casinos, maybe lose some money, you know. It's more for the experience, right?
So we start to see people actually react to social conversations. So we have 20 participants coming in to do this physical collaboration task. Out of 20, 18 of them engage in conversation with the robot. Overall, it's pretty high response rate, right? 86% of people respond, and they respond in various ways. Could be very long sentences about the question the robot asks, as the example I show you. What's interesting is that they are not just responding, but they actually start to have a careful engagement, right? So they ask questions back to the robot. So here's another example. Robot, I don't know, do you like to play games? I like to play Tetris. If you have ever played that, can I get, so they didn't forget about the task, can I get another yellow pipe? Getting it now? No, I have not. Person will say, oh, you might like it. Can you tell me more about it? And then this person just go on to explain the task, and then with gestures, oh, just like, different shapes, pipe, drop it down, and you will click it once you have crossed the line. And they even made a movie about it, right? So we start to see people have this meaningful engagement, answer the question, not just the question the robot asked, but also disclose some of the things they know about the questions. So we start to think, okay, this is interesting. There's an interesting opportunity here to make the workplace more enjoyable. But it's not. It depends on the setup, right? So we also have this large language model powered voice assistants deployed into older adults' home, right? So we have this Echo device with Alexa skills. We integrate ChatGPT with that Alexa skills so that it can answer a variety of questions. We build this little device. We have a little recorders there. Obviously, get their permission to record. But we get very organic interaction. Because if you just only get transcription coming from Alexa skills, usually you will not get the organic interaction and reactions. So we put these systems out to people's home for a long period of time. I believe it's a month. And then we have a lot of organic interaction between how older adults interact with this LLM-powered voice interaction. So I'll play a clip of that and tell you some of the things that we learned.
Questions do you have?
If
that's all, until next time.
No. Alexa, please give me more time to answer.
Give me a second. Of course. Take your time. I'll be here whenever you're ready to continue the conversation or if you have any more questions.
In a patient that is panhypopituitary, how important is it to work up a fever?
I'm on it. If I understand correctly, you are asking if it is important to work up a fever in a patient who is
So we get a lot of data like this. A lot of things we learn from this. If you just combine these two technology, voice assistant and large language model, it doesn't necessarily mean it will work okay, right? So the first thing we found is older adults, for example, they need more time to react. And then a lot of voice assistants, they don't take that into account. Second thing that we learned is a lot of language model output is very verbose. They are designed for textual interactions, but not for voice interactions. So we start thinking about, if we are really serious about using large language model as a driving device for conversation, then we need to rethink about how to integrate this into situated interactions. So I think there's a huge opportunities here to bring in this social aspect, social conversation into a close collaboration. All right, so next one we talk about is, collaborations start to form, people start to work with your machines, but inevitably there are mistakes. Right, so errors are unavoidable, unexpected, and can have undesirable impact to the task. Right, so as an example of undesirable impact, here's one example where we have, again, robot helping humans to cook. And the robot will just provide different ingredients for the person to cook. All right, so the robot will say, okay, now chop and add sausage to the pot, and the robot pick out mushroom, give it to the person. And the person recognizes the mistake, say, no, what if it's wrong? But then continue to get the mushroom, chop it, and then put it into the pot, right? So people, even though they recognize the mistake, but they complied. And we are not just seeing this in toy example in the lab like this. We recently did a large-scale study with human expert radiologists to read X-rays, and we manipulate the AI quality. Unfortunately, human experts still comply in certain degree. So it's important to recognize errors and manage them properly before they have negative impact on performance. A lot of errors in human-robot collaborations is just unexpected, right? So I'll just play this as an example. And again, this is robot picking up pipes and building some structures.
Give me a green pipe.
The person say, "Can I have green pipe?" Robot went on, pick the green pipe. Accidentally drop it. This is not pre-programmed. It's just like, as a byproduct of manipulation. One thing we learn is people react to mistake. Pretty robust. We actually see this in a variety of situations, right? So when robot make a mistake, people have this social reaction, like surprise, sometimes laughed, confused, just all sorts of reactions. And not just with physical robots. We are seeing this for smart speakers. When smart speakers make a mistake, people also react, right? So they might laugh, they might confuse, they might just like stretch their head. So we thought, okay, this is an interesting trend and very powerful cue. What if we can use this to detect errors, right? So a lot of error detection in prior work is to look at, you have a good understanding of the task situations. Any behavior that deviates from that task model is an error. But then we realized, okay, social signal is pretty flexible. It's very robust across platforms and situations. So we start to use that as a way to detect errors. So in our simple setup, we have cameras to capture human reactions. We extract their facial expressions, action units. Did some very, very simple modeling process just to do some thresholding to say whether or not this instance is a mistake. And even with this very simple modeling, we are pretty good at, successful at identifying mistakes by the robot. So here's one example of the same setup. The robot will fetch different task items. The person takes the task item and build. So here we go.
Give me a green pipe.
I think the audio is a bit muted, but essentially request the pipe. And miss it. And the person,
No.
and the robot detect that, and the robot said, "Am I doing all right?" And the person say no, and then initiate the recovery process. So that is the early detection that we are aiming for, right? Not waiting for the user to say, okay, you are making a mistake. We use that and say, hey, detect that and say, am I doing all right? If not, then I'll recover, right? So this is a demonstration of how we can use social signal as a way to do early detection. We are in the process of actually run a study on this, a full-blown study to really see the benefit of these early detections on collaboration. But if you think about detection, it's only the first step in error measurement, right? Once you identify errors, what do we do, right? So the next thing we look at is how do we do mitigations, right? How to repair the lost trust. So I want to use this example as a way to introduce mitigation. This is not robots, but smart speakers, custom smart speakers. The arrow that we're looking at here is intent recognition arrow, so homonyms. So this is what it looks like.
Phoenix, add self-rising flower.
Okay, I found a dozen roses. Should I add to cart?
No.
Let's try that again.
Phoenix, add baking flour.
Okay, I found King Arthur flower. Should I add to cart?
So this is the arrow that we're manipulating, and then you see that the person react to the mistake. But the thing that we're interested in here is, given this arrow, how do we recover the trust? So we look at how to apologize and how to build the trust back. We look at two different elements. One is attitude, the other one is blame assignment. So it could be a serious versus casual attitude, or you take the blame or shift the blame, right? So if you're a serious attitude, so I'm sorry for the inconvenience, versus casual will be, oh, sorry for the mishap. Taking the blame will be, I have difficulty distinguishing between homonyms, or I'm confused at the item, versus shifting the blame would be, the engineering team must have done something in the system update last night, right? So shift the blame to the system team. So we just try different reactions for the voice assistant and to see how people react to these different mitigation strategies. So what we found is you really need to own your mistake seriously and sincerely, right? So when you are very serious about the mistake, you apologize for the mistake and you take the blame. People think the system is more intelligent, it's more likable, and overall are more satisfied with the service coming from the voice assistants. So we started to look into what are the good strategies for machines to handle mistakes. But one thing that we started to learn is it's very tricky to get this right. We actually see some biases in these interactions. If you think about a lot of voice assistants, they are programmed to gender like female, and that has some of the consequences. So I'll show you one example here. So similar setup interactions. What we found is when there's a mistake, male participants interrupt the voice assistant more than female participants. Also depends on the mitigation strategy, right? So if the voice assistant just try to apologize versus trying to compensate by offering you gift card, right? I make a mistake, I'll give you some big gift card. Male participants interrupt the compensation agents much more than others. And this is independent of voice assistants gender. So we look at female gender voice assistants, male gender, and neutral. So we start to see some of these biases in the way people interact with the voice assistants. So I'm going to play this video. It's kind of extreme, but that just shows you some of the interruption that we're seeing.
Okay, I found green tea clay face mask.
Yeah,
Should I add to cart?
Yeah, add that to cart.
Got it. Item has been added to your cart. I will give you a $10 credit that can be applied to your future purchases with us for the inconvenience caused.
Oh my god.
So obviously this is a very extreme example, but we are seeing just more interruptions coming from this this setup. So I think this is based future investigation into how do we think about designing mitigation strategies and how do we think about gender dynamics play into this. This is ongoing directions. We are in the process of mitigation. We haven't got into repair yet, but if you just think about error management, there's so much that needs to be done to have a successful collaboration. So I talk about some of the work in this space, thinking about onboarding, thinking about task sharing, shadowing, talk about some social interactions, and think about ways to think about errors and how to mitigate those errors. It's a very rich space, very nuanced. There's a lot to do. Some of the things that we're thinking going forward is, if you think about a lot of HRI, human-robot collaboration work, or human-machine interaction work, it's one person, one machine, fairly prescripted to a certain degree. But human collaboration is very ad hoc, in the sense that they don't form a plan. The plans come together as it goes. Right, so we recently got this support from NSF, and to look at this ad hoc collaboration, how do we understand people's ad hoc collaboration and translate those principles into human-machine collaboration? So here's our early data collection for trying to understand human ad hoc collaborations. So we have a very large-scale bunk bed task. We project the task on the wall. It doesn't specify the step, but just tell you this is the final output. Go and build, right? And we just collect data on how people build this ad hoc, task ad hocly, right? So people build up the plan as they go. A lot of multimodal communication, a lot of parallelism in terms of shared task load, a lot of small talk, social interactions, a lot of implicit help. When the pipe is too long, the other person will help the person to finish it. So we're getting building this data set of trying to understand how people work together as a large team in the ad hoc format, and then hopefully translate some of our learning into human-robot collaboration. So we are excited about this. Another direction that we're pushing forward is understanding the reliance, like human reliance on AI or robots in general, right? As I showed you earlier, if we don't do this right, there will be negative impact. So how do we do online reliance estimation and calibration, right? So we start this with a simple 2D task to look at how people solve the problem. So this with eye tracking, each bubble means fixations. They will do the task. As they do the 3D spatial reasoning task, they will fill out the answer. Halfway through, we will provide AI suggestions. And we want to see how they use the AI suggestion during this process. So what we learn is, based on how much time you look at AI suggestion and when you look at AI suggestions, that will predict your reliance on the AI suggestions. And we thought, OK, this is great, but this is a total example. So we started to bring this into a more serious domain where we have a radiologist to look at this X-ray, and then, again, collect data, and then use this as a way to understand how much the radiologist is, quote unquote, relying on the AI suggestions. Over-reliance, under-reliance, and we will change the AI presentation a little bit to calibrate the behavior. So this is ongoing, but essentially looking at how we can estimate reliance on the fly in order to provide meaningful intervention to have successful collaborations. Lastly, another line that we are very passionate about is to do more longitudinal field work, especially for home care robots for older adults. I started Hopkins, really want to do this, realized there are so many infrastructure that needs to be built in. 2 years in, pandemic hit. I was like, oh, great, can I do anything? But about 2 years ago, we started to be able to pick this up. We haven't done much yet, but we started to bring robot systems to people's home, get their feedbacks on how they would program. Example I show you, we deploy voice assistants to know how the natural interactions. We bring in manipulators just to understand what kind of things that we need to care about. Some of the example I talk to people individually, but not a lot of concrete results from this yet. But going forward, we want to continue to build on this because I believe in learning from the people in the field will drive a lot of innovation and research back in the lab. So we'll continue to push this. And I think this will give us a lot of insights to think about designing collaborative robots for people. So with that, I thank you for your attention, and I'll be happy to take questions.
I'm curious about the social interaction aspect. You mentioned either facial expressions or like small talk and how you interact with a robot. I was wondering if you guys have done any like study or research about like say like a long-term user? I can imagine at least intuitively that your facial expressions, like if the robot makes a gaffe the first time, you'd be surprised or find it funny. But if you like work with it every day, like a month later, you just
still the same joke. Like, no, that's a good question. We haven't done that yet, but that would be something that we're interested in, is that repeated interactions, right? So people are really good at this, adapt, bring in their understanding of the person. So what we're showing right now is just early exploration. Is there any benefit of adding this social element into the physical collaboration processes? We are seeing some benefit, but then the next question is, how do we make this robust? How do we make this carry over to multiple sessions of interactions? But yeah, I mean, we haven't done it, but I think that's very meaningful future directions.
For the like ad hoc collaboration, like I guess that was future work, but when you're, I guess, kind of empirically observing how like people do tasks and like collaborate on like a team project, like how do you kind of learn that organization? Because it seems very like hidden. Like, yeah, I guess like what work have you done so far to even kind of like get down at that hidden structure?
So the concrete answer, not much. But the way we think about it is, we are just capture the whole posture. We are also have each participant wear this first-person view to see how they manipulate the object. So we have this hierarchical information coming in, the fine-grained manipulation, and also task-level collaboration. Obviously, we also have audios. So the way we would go about this is we will define a language of collaboration first, like language of collaboration, and what are, where do people do communication, where do people do implicit help, where do people do repair. And from that, we'll build down more details hierarchy. So that's the way we think about it. We talk about it in the proposal, but in practice, we haven't done much in terms of actual carry this out. But it's pretty. If you look at the ad hoc collaboration, it's pretty rich, right? That people do different things. So I think one thing we will do is to scale back a little bit. Say, maybe we'll start with something simpler as opposed to go all the way to this bound back setup. Yeah.
In that same context, I was wondering if you've thought about the collaborators having way more different abilities versus, like in this case, everybody's somewhat same level expertise on that task versus a robot and a human. Vastly different.
Yeah, so I think I talked to someone else earlier. So as a way of that, we also try to simulate less capable people. Right? We have people coming in, even though they are able people, we just ask them to, their arms got injured or something. So we essentially strap their hands, they're not able to use one hand, and to see how the other person will accommodate that artificially limited ability, right? So that's the way we think, we simulate limited robot capability. So the goal is to, if we can have this capacity awareness, that will come into play later on in the modeling process. But yeah, I mean, robots less capable than people. Yeah.
Actually, so I have another question about earlier you mentioned using language models to actually program the robot. So I was wondering, so for that, like when you said the errors in terms of the programming, I was wondering how you, I guess, check the errors. Do you just like run your thing or like look at the code? Because I was thinking let another language model interpret the code and see like what steps in a more readable human format might help that loop as well. So I was wondering how I was exporting that.
So we didn't use a second language model to double check, but I think that's a good idea. What we did is, because we run this multiple times, we saw there are patterns of errors coming from large language model. We actually empirically build heuristic about common errors, right? So missing library and all that. So that's why we can write a verification script to check. I think another thing, I think human readable, I think the output right now, we also prompt them so that the model will give you comments, like what this next block of code means, right? So it's interpretable in that sense, even though the code might not be correct, meaning like, for example, open the gripper, middle of the movement. So it's fairly readable from the user point of view if they want to read the comments.
Have you done, do you just take that as is as the prompt, or have you done any prompt engineering type thing, like where that's part of the prompt, but you also add information about like is it a robot, is it a function, which just seem to work well in some of our experience.
Yeah. So one thing that we try, which is like reinforcement, you have to use the library code that we provide you. So whatever the user provide, we'll add that in the beginning. I think that helps. I think we also add something after it as a ways to, I forgot what exactly we added afterwards, but we did something like patterns. Empirically, that works. But a lot of things that we learn from working with large language model is very empirical. Like we don't necessarily know why it works. It's just like we tried many times and it worked.
Yes. For the experiment where you're doing small talk with the robots, I'm curious, I don't know if you gathered this kind of information, but did people come away feeling like their interactions were genuine? Did you kind of learn anything about that, I guess?
Yeah. So very good question. We did some interviews afterwards. So some of the people, they just got really into this, have meaningful engagement and conversation, but some of them, they don't. And the reason it is because some of the questions that is not necessarily personal, like to that participant, right? A lot of human small talk is that I know you, and therefore I will talk about the things you may care about. But for this, we don't have a human model, if you will, right? So, and that's where multiple repeated interaction will come into play, right? So, if we really want to build this social capability, then we need to have a good sense of what the person cares about, and then you want to change the conversation a little bit. But right now, there's no. Yeah. Yes.
For the gendered voice assistant experiments, did you do any kind of separation when it was women participants reacting to women versus male voice assistants versus male participants reacting to women versus male voice assistants?
We do gender balanced. So we have female assistants, male assistants, gender neutral assistants, male participants, female participants, and the third category is a few participants, so we don't really able to draw connections there. But we do gender balance. Excuse me.
Any final questions? All right, let's thank Chanmin one more time.
Thank you.